I skipped the question there. All right. Radiation from the sun reaches the Earth above the atmosphere at a rate of 1,350 watts per meter squared. Assume that this is a single electromagnetic wave and calculate the RMS value of the magnetic field. So let's rewrite the equation again for the RMS value of the magnetic field. It is, I don't have these memorized. If you do a lot of practice problems with these while you're taking the class, you'll probably memorize it. So don't worry too much if it doesn't immediately come into your head. So they're asking for RMS magnetic field. So this is what it looks like. They've told us the intensity is 1350. Speed of light is 3 times 10 to the 8th meters per second, and then this little U0 thingy, that's the permeability of free space, 4 pi times 10 to the negative 7. So if we solve for RMS magnetic field, we get about 2.378 times 10 to the negative 6 Tesla. 10 to the negative 6 is the same thing as micro, right? So that unit that looks kind of like a U. Micro. So we can replace the 10 to the negative 6 by micro Tesla. And again, units of magnetic field are always going to be Tesla or some derivative of that, like micro Tesla in this case. All right. So I'll go ahead and try this example, and keep in mind the definition of the definition of intensity, which is really power over area, which the units of that would be watts over meters squared. So go ahead and try this one. All right. So basically the way we do this problem is that we have a light bulb, which is our light source. So what's going to happen is that this light bulb is going to be emitting light in all directions. So light would be emitted in all directions. And even out of the page, if you want to do out of the page in physics, you generally put it like this, as in an arrow coming toward you, and then an arrow going into the page looks like this. As it goes in all directions, the light waves kind of go out in the shape of a sphere, if you can think of, in all directions, right? And for a sphere, to find the area of the sphere, because we need to find area, we're going to go ahead and use the equation that is like this. So the area of sphere is 4 pi radius squared. So we're trying to find the intensity, because what we really want to find is the maximum value of the electric field. So if you use the equation for that, it looks something like this. Intensity, or at least average intensity, is one over 2 permittivity of free space, speed of light, maximum electric field squared. We have these two because they're constants, but we need this, right? Now this intensity is going to be equal to power over area. So we can rewrite this as power over area. So the way you find the area is by doing this, right? So we have a light bulb and it goes in all directions. We're told that the distance that we want to find the electric field at is 2.5 meters from the light bulb. So the radius in this case would be 2.5. Because if you were to imagine this, I can only draw it in one dimension, in 2 dimensions, but it's a three-dimensional thing. The light bulb's in the center, right? From the center of the light bulb to like the outer surface of the sphere, if that's 2.5, then that basically is the radius of the sphere, and that's where we're trying to find the electric field if you want to see it drawn out. So for area we get something like 78.54 meters squared. So that's going to go, let's see, it's going to go on the bottom side of this. Power they give us, it's 100 watts, right? That's pretty simple. Power is always in the units of, generally always in the units of watts or joules per second, something like that. These constants, this permittivity of free space is going to be 8.85 to 10 to the negative 12. Let me make sure it was it. Yeah. Good. And then the speed of light is 3 times 10 to the 8th. And then now we just need to find this. So now you just do a little calculator action. So we get electric field maximum is 30.97, and this is going to be in the units of either newtons per coulombs or volts per meters. All right. Next question asks, a 15 milliwatt laser puts out a narrow beam 2 millimeters in diameter. So the question now is, what is the average or the RMS value of the magnetic field at that point? So go ahead and try this. It's a little different from the last one, but same principles apply. What you would do in this situation is you would kind of imagine a laser. I'm going to draw this. And the laser goes out. Right. Now this laser is going to have, it's going to converge onto a point where it's going to be circular. So it's not spherical, but it's circular. And we can draw the laser a little bigger so we can see it better. Let's say this is the laser. We have the, let's say it's hit like a wall. So we have a wall here. Now, we're given the diameter of this circle, of this laser, really. It's 2 times 10 to the negative 3 meters, or 2 millimeters, they tell us. So what we can do is use that information to find the area of this circle. Area of the circle is pi r squared, right? Yeah. So to find the area of the circle, pi and then r, which is, we have the diameter here, but we want radius, so divided by 2. So that's 1 times 10 to the negative 3, and that's squared. So then we get we get pi times 10 to the negative 6, basically. Then we want to find the intensity, right? And intensity is defined as power over area. Then we're going to use that to find the average magnetic field. The average magnetic field relative to the intensity is like this. It's going to be speed of light, permeability of free space, and then magnetic field average squared. So now that we have that information, we can solve for the intensity. So power is 15 milliwatts. So the power here is 15, and again it's milliwatts, so 10 to the negative 3 watts over 3.14 times 10 to the negative 6 equals speed of light times the little magnetic field constant, which is 4 pi times 10 to the negative 7th, and then magnetic field average squared. So if we use your calculator here and solve this. The answer will be something close to 4.47 times 10 to the negative 6 Tesla, or 4.47 microtesla. Excuse me, microtesla. So that's the answer here. If the electric field of an electromagnetic wave has a peak value of 2 volts per meter, what is the peak value of the magnetic field? This is an equation we haven't gone over. You can try and derive it through what we just did, but there's a very simple relationship between them. And it works like this. Electric field is equal to the speed of light times magnetic field. So if the electric field is 2 volts per meters and the speed of light is, as it is, 3 times 10 to the 8th, then the magnetic field is just 2 divided by 3 times 10 to the 8th. So it's going to be 6.67 times 10 to the negative 9 Tesla. Maybe you can call it nanotesla as well. And so this is for peak values. For RMS values, it also works. This was just a peak values example, but you could also do this as well. That also applies. All right. Now this is a bit of a different question, so try this on your own. If you can't get it, then just watch how I do it. So we're asked how much energy per hour is transported across a 1 centimeter squared area by an electromagnetic wave whose electric field has a peak strength of 21.5 volts per meter. What we want is energy per hour. Now we have a couple of concepts. Excuse me. A couple of concepts we can use. We can use intensity, which gives us power over area, which again, power is basically energy transferred per second. So if we can find intensity and then, you know, extract out of that the energy per second, we can actually find the energy per hour, because they're asking for energy per hour. So how do we find intensity? So they give us the peak strength of the electric field. That will be enough, right? So the average intensity is equal to 1 over 2 E naught, and then speed of light, maximum value of the electric field squared. Now E naught is going to be 8.85 times 10 to the negative 12. Speed of light will be 3 times 10 to the 8th meters per second. And the maximum value of electric field in this problem is 21.5. And we're going to square it, and we will find the intensity. So intensity is 0.6136 watts per meter squared. All right. So now that we have this value, we can do a couple things. We need to get the energy per second. So we need to really like extract out this area part. We're given an area value of 1 centimeter squared. Be careful when trying to convert this into meters squared, right? 1 centimeter squared area, they're telling us. We know that 100 centimeters is a meter, but in this case they're squared, right? So you have to square all of it. So it'll be 1 on top, and so if you do this, you get 1 times 10 to the negative 4 meters squared. So be very careful on that. I think that's where people might mess up. So since you want to get rid of this, you're going to multiply. You put this on top so that the meters per second cancel out. And you're left with 0.6136 watts. Watts is the same thing as joules per second. So you've discovered joules per second. So 0.6136 joules per second. We can turn this into hours. We know that 60 seconds is a minute, and we know that 60 minutes is an hour. So 1 minute minutes cancel out, seconds cancel out. We get joules per hour, which is energy per hour, what we want. So this will be 2.0896 times 10 to the 3 joules per hour. So that's how much energy is being transferred through a 1 centimeter squared area by this electromagnetic wave that has an electric field peak strength of 21.5 volts per meters. So hope that was a helpful video for you, and thank you for watching.